This is an overview of how to use stepwise regression to develop an initial equation for multiple regression and then to try to validate it with another independent sample using hierarchical regression. To do this, the first thing that we have to do is we have to take a random sample of the data. This data set that I'm working with has 200 cases. So the first thing that we're going to do is we're going to split this data set in half using random sampling. So we're going to create a random sample of exactly 100 from the first 200 cases. And click Continue and click OK. I'm then going to open up this data set. I'm going to save it under a new name to my desktop. I'm going to call it Course Documents Regression Data 1 Sample. Save it. Then I'm going to revert. I'm going to open up the reverted saved file, open up data. Click on open, revert to saved, and we'll open up my data set. When I look at the data, I now have a filter variable collect in which 100 of them will have a filter value of 1 and 100 of them will have a filter value of 0. I'm going to generate a stepwise regression using half of this data. The challenge with stepwise regression is that it may take advantage of type 1 error rates. It kind of fishes for the best set of predictors, and those best set of predictors tend to be sample dependent. So part of what we want to find out is whether or not the linear equation that we generate using stepwise regression can be validated with an independent sample. So we're going to go to Analyze, Regression, Linear. We're going to predict science score from gender, reading, and math scores. Our selection variable is going to be, I'm going to send our filter variable over here to selection and click on rule, and I'm going to run my stepwise regression using a value of 0. So you type in 0 and click continue. The method I'm going to use in this case is going to be stepwise. I'm going to click on statistics. I'm going to want descriptives, collinearity diagnostics, case-wise diagnostics, and I'm going to click continue. I'm going to check for some basic homogeneity of variance issues. I'm going to send Z predicted to X, Z residual to Y, and I'm going to get my probability plots to see if the residuals are normally distributed. Click continue and click OK. And this will give us the equation for the best predictors. And what we can see is it went through 2 iterations. The final adjusted R-square was about 0.464 or 0.453, so about 45% of the variance in the dependent variable was explained by the best set of predictors. We see that the prediction model is explaining more than 0 variance. And we see that math and reading scores both were significant predictors. Math entered first, then reading entered, and then no additional variables entered into the equation. So what we would do in this case is we would see that with these two variables, we're explaining about 45% of the variance, 46.4, 45.3 adjusted for sample size. We can look at the rest of the analyses. We're not going to worry about them primarily right now. So then I'm going to go back in. I'm going to run another regression. And this time, I'm only going to use two predictors. I'm going to take female out. I'm going to use enter to force these two variables in. I'm going to change my rule now to 1. And I'm going to hope that with these two predictors in there alone, that my model explains about the same amount of variance, and that the slopes are approximately equivalent when we have just those two predictors. Click OK. We look down to the adjusted R squared, and we can see that we're doing a little bit better this time. Instead of it being 45%, we're up to about 49%. So the model is about 4% better with the validation sample than it was with the initial sample. We could then go and look and make comparisons of the actual betas and the unstandardized slopes to see if they were comparable with this analysis. But that's basically what we would do to work on validating a stepwise regression with an independent sample.